So now let us step back and look to the terminology we are going to use when we are dealing with Paxos. So Paxos uses 3 different types of roles in the system. Each node could actually play all the roles. But so we have a role of proposals, and proposals are nodes or processes that will try to attempt imposing the proposal on a set of acceptors. And we have the set of acceptors which accept values or may accept values issued by proposals. And we have the set of learners. The set of learners are, these are roles. So the set of learners will decide depending on the acceptors of acceptance. And just to make it briefly is that whenever a majority of acceptors agree on a value, this will be the value decided upon from now on to in the future. So what do we have? We have actually a quorum approach. We have a set of nodes or a set of roles, which is, we call in this case, the acceptors. And we say that if a majority of acceptors accept a value, then this value, V, will be the chosen value, and it will never change. This is the value that will be the result, the output, the decision of the consensus algorithm. So a majority of these, once a majority of acceptors accept a value, this is a chosen value. Remember now this terminology, chosen value. And learners will try to decide the chosen value. They try to learn the chosen value, and they can only decide on this value. Good. So one issue then is when an acceptor accepts a value. So ideally we have a single leader, a single proposer that is elected by the leader election abstraction, and at least our algorithm should provide obstruction-free progress, which, if you remember, means if a single node executes the algorithm without interference, it will make progress. That's what we want. So we want our algorithm, which is in this case the Paxos algorithm. We are trying to understand the algorithm gradually, step by step. So somehow we have to guarantee the following. For this algorithm to make progress, we have to have the following property. We call it here an invariant, because we don't want this to, we want this always this property to hold during the execution of the algorithm. And the property we want to hold is P1, which says an acceptor accepts first proposal it receives. So if there is a single reader and an acceptor accepts its first proposal it receives, then we will have a majority of acceptors accepting the value proposed by that leader, and that will be the value chosen because we have a majority of acceptors accepting this value. Okay, and that of course will guarantee progress. So let us now see what would happen if we have this simple algorithm. The algorithm that proposers just propose and acceptors accept the first proposal. So here is a situation. What do we have here? We want to satisfy this property. An acceptor accepts first proposal it receives. We have 5 acceptors, which would mean a value is chosen if we have 3 that accept the same proposal. So here is a situation which the following can happen. We have a situation where a node, this in this case, or a process, P1 proposes red. We have 3 nodes that accepts red, which is the first proposal. And we have node 5, which proposes blue, and 2 nodes that accept blue. Very nice. at this stage like this, so really we have a majority that accept red. But if P3 fails, we have a situation where we have 2 reds and 2 blues. So what is the value chosen? At any point here, it is impossible to know what is the value chosen. So this simple strategy does not really work. So we have to refine it a little bit. So let us go. So what we think what we have to do is that we have to allow proposers to change their mind and propose new values. They have to restart again. We are stuck in this situation. So what we need is we have to force restarting of proposers. So let the node change their mind, basically. So let us see what we can do. How to enable restart. So until now we say, okay, a proposer can try to propose again. And if you can propose different values, we are going to make sure that we have to distinguish between the proposals. And so we attach a unique sequence number to each proposal. And we call the sequence number, it's often called actually a ballot number. So we attach, and we make each proposal attach a sequence number that is monotonically increasing. The ballot number should be monotonically increasing once you issue multiple proposals. Okay, and how to achieve this? A possible implementation is as follows. Node 1 uses ballot numbers 1, n plus 1, 2n plus 1, 3n plus 1, where n is the number of nodes in our system. Node 2 uses 2, n plus 2, etc. And node 3 uses 3, n plus 3, etc. This is one possible implementation with unique ballot numbers. Another possible implementation is to say that the ballot number or a sequence number or the proposer number is actually a pair which has the local clock plus a node or a process identifier. And we assume that the local clocks of the different nodes are loosely synchronized. So these should not, doesn't matter if they are exactly synchronized. This is monotonically increasing, and they are loosely synchronized, and you can actually do a simple algorithm to loosely synchronize clocks. So, and of course, we now distinguish between proposal by lexicographic order. So if the clock collides, we choose the lowest IT. So what do we have now? We have a situation where nodes can restart and propose again. So let us see. So here's an example. And we're going to see that we have a problem with this. So here is a situation where P1 proposes red with a proposal number 1. This was accepted by 3 acceptors. So at this point, there is some kind of majority for that. Then P1 and P2 fails. Then we have P5 that proposes the value blue, and fine, and it is accepted by the 3 nodes, P3, P4, and P5. But now we have a strange situation, which actually we are violating agreement, because at this point here, a learner may decide on red, and at this point here, a learner may decide on blue. So we are violating agreement. So we have to have a mechanism to ensure agreement. Let us look again. What is our problem? So our problem is, from the previous slide, is that if restarting is allowed and proposals propose, a majority may accept first red and later may accept blue. So we still need property P1 to accept first proposal. But the issue now we need another stronger property to ensure agreement. Okay, and what is the property that we can use to ensure agreement? Here is a property P2, which says if a proposal is chosen, every higher number proposal chosen should have the same value. So if a proposal is chosen with value V, then every higher number proposal should be chosen with that value V. Remember, what we want to avoid is the following. We want to say, here we have a proposal, right, that is chosen. We want to ensure that every proposal that is accepted after that should have the same value. This should be red, not blue. So this is a property that we would like to achieve. If a proposal is chosen by a majority, every higher number proposal chosen by a majority again should have the value V. So here we are. We are in a situation where we came to these two properties that we require, or invariants. An acceptor accepts first proposal it receives, fine. And if V is chosen, every higher proposal chosen should have the value V. So again, to remind you, P1 ensures obstruction-free progress and validity. And of course, property 2 ensures agreement if we can implement it, of course. So that is where we are right now. And integrity is easy to implement. Anyone that decides has to remember that he has decided and does not repeat his decision. So let us try now to see how we can implement P2. So we have this property, P2. We want to know how to implement it. So maybe here is a weaker property that we can implement, which is basically P2A, and the property is if V is chosen, we would like that every higher proposal accepted by an acceptor has the value V. And if every higher proposal have the value V, then in the future the value V will always be there, and there is a majority of acceptors that will have the value V. So this P2A in fact implies P2. So here we are. If the value V is chosen, every higher proposal accepted should have the value V. So, and here what we have, and here why we need P2A. Here is a situation where the value red is chosen here. We want to avoid now the situation that if we can satisfy this property, it will not be possible to accept the blue value, okay, even if it has higher proposal. So now we are in a situation where the following is true. So how to implement if V is chosen, every higher proposal accepted has the value V? You see, we have a situation here where acceptors can accept values, and they can accept values with higher proposal number. And we would like to avoid a situation where a value is accepted, in this case the value blue is accepted after a value which is red is chosen here. So how to avoid this? The way to avoid this is to do the following, is that if we prevent values with different value being issued, then we can avoid this situation. So what we want to say is that if a value is chosen, we would like that every higher proposal issued has that value. So, and we avoid the problem that we had. We cannot propose, as in P5 here, the value 5. All right, so okay, so let us have now just a roadmap where we are right now. Remember, before we go to that roadmap, now if each value issued after a value is chosen has the value v, then every value accepted after a value is chosen will have the value v, and we are now in this situation. We want to satisfy that if a value is v is chosen, every higher proposal chosen has the value v, and we said this can be satisfied if a value is chosen, every higher proposal accepted has a value v, and this can be satisfied if a value is chosen, every higher proposal issued has the value v. So that is what we have right now. We are in a situation where P to B implies P to A, so this implies that, and we know that this implies this, and therefore this now implies this. Okay, so we need a way to implement or to have an implementation that has this property. If a value v is chosen, every higher proposal issued has the value v. To do this, we will go and take one step further, and the step is actually we try to satisfy this property instead, which is P to C, which says, now we're interesting about valued issued now. We say if a proposal is issued, then we would like to have the following property. The property saying that there is a set of majority of acceptors that have either this property, no one in S has accepted any proposal less than n. So when we want to make sure that if a proposal is issued, either no one in this majority of acceptors have accepted any proposal less than n, it means they have not accepted any proposals, or that v will be the value of the highest proposal among all proposals less than n, among all proposals less than n accepted by acceptors in S. So this second condition says we want to make sure when we issue a proposal, we can guarantee there is a set of acceptors. Maybe they have a value, this one has a value v1 with n1, this has a value v2 with n2, this has a value v3 with n3. Among, say, 5, there are 2 more, but these are majority. We want to make sure that if some proposal proposes and have this proposal value, it should be the value with the highest proposal number among these majority of acceptors. This is a majority of acceptors. For example, if n3 is higher than n2 is higher than n1, so you want v to be equal v3. Fine. So we want to guarantee that if a proposal issues a proposal with value v, it will be a value of 1 in a majority of acceptors. This is the one with the highest proposal number. Now, if you think about it, so if a value is chosen, there will be a majority of acceptors that have this value. And whenever a proposal tries to issue a value, it has to inquire about this value from a set of acceptors. So now we want to see how to implement P2C. So in particular, we have a proposal that issues a proposal number n with value v, and we want to guarantee that v is the value of the highest proposal among all proposals less than n accepted by a majority of acceptors, or accepted by acceptors in S, and S is a majority of acceptors. Okay, So how can we do that? The way to do it is that a proposer needs to first go into a prepare phase. We call it prepare n phase, before issuing the proposal number n with value v. And what it has to do, it has to extract a promise from a majority of acceptors not to accept a proposal with a value less than n, and each acceptor sends back its highest numbered accepted value. And from these values, the proposal can choose the highest among these. So if we do that, we can guarantee that because the acceptors promised not to accept a value less than n, that v is the value of the highest proposal among all proposals less than n accepted by the acceptors in S. Okay. So this is the algorithm that we need to guarantee this property. All right. Now we are in a position to look to the whole algorithm, which this we call it Abortable Consensus. So a proposal picks a unique sequence number n, that's monotonically increasing of course, and send a prepare to all acceptors. An acceptor, when it receives prepare n, promises not to accept a proposal, any proposal numbered less than n, and it will send the highest proposal accepted with number less than n. Okay, that is its promise. So now it has to remember not to accept any proposal less than n. A proposer, upon receiving a majority S of promises, it will pick the value v of the highest proposal number in S, and if none is available, it will pick freely. If that is fine, it means that in this set of acceptors there is no value accepted less than n, and then it will issue an accept n v to all acceptors. Okay, so either pick freely if the acceptor didn't accept anything, or pick the highest value. Now when an acceptor gets this accept message or accept value v with proposal number in, if it has not responded to another prepare with a higher number, then it will accept this value. So remember, if it has promised it in the previous phase, it has promised to accept, not to accept a proposal less than n. So here again, if it has not responded to a prepare m was higher than n, then it will accept this proposal. Otherwise, it will either ignore or reject the proposal. According to the algorithm, can either ignore or reject the proposal, which is fine. Now, if this proposer gets a majority S of responses, and these are ACK responses, then it knows that a value has been chosen, because it means that there is a majority of acceptors that has this value, and this value will never change in the future. Okay, and therefore it can decide on V and broadcast the value. It can either abort if it gets a NAC, or if it waits for a longer time, it can abort again. Or if the proposal is no longer a leader, it can just abort. Okay, thank you.